after briefly introducing why we still need analog IC design, then I need to tell you the truth. Analog IC design is much more difficult than digital one. Why? Because there are quite many aspects to make analog design more difficult than digital design. From the very beginning, for digital circuits, they only concern speed and power, that's it. All right? But for us, we not only concern the same thing, the speed, very important, power dissipation, maybe right now even more important for portable devices, just like iPhone, iPad, blah, blah, blah. However, we still need to pay attention to the other aspects, just like gain, precision, supply voltage, high or low bandwidth, blah, 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 all of them. All right? And also that our circuits are more sensitive to noise, crosstalk, interference than digital signal. Why? Why? Because I told you already, for digital one, they have 50% for threshold. Okay, above it, 1, below it, 0, that's it. So any kind of interference, noise, blah, blah, here, right? Ew, who cares? Only if the spikes, okay, no more than 50%, then they still get the correct signal. All right? And also they have the so-called signal regeneration. 他们的讯号可以重生. Why? Oh, very easy. For example, a digital buffer, usually composed of 2 NAND gates. All right. From the beginning, for the input, it has a quite noisy input, and after that, you can get perfect signal, perfect digital signal again. We call it signal regeneration. Is it possible we have some kind of analog buffer? Yeah, you have some kind of noisy input, then you get the perfect output. Oh, forget about it. Nothing is possible in analog domain. Maybe you think, we have the so-called filters. Yeah, for such kind of dirty, noisy input, we can apply some kind of low-pass filter, blah, blah, blah. Oh, yeah. In theory, we have such kind of low-pass filter. Yeah. Okay, please pay attention to that. We have positive spectrum. We also have negative spectrum. And they are symmetric to each other. The only difference is the phase. The phases are reversed. Okay, that's it. Magnitude the same. Phases are reversed. What does reversed mean? Positive and negative. 相位颠倒. For example, here, positive 90 degrees. There, minus 90 degrees. That is the definition for reversion. Okay? Anyway, anyhow, that is what we expect to deal with such kind of high frequency noise. We can apply such kind of very good low pass filter to filter out all the high frequency noise. Is it possible? No, sorry for that. That is the ideal case. But again, nothing is ideal on Earth. I mean, in analog domain. So what is the real shape of such kind of low pass filter? It looks like that. I only plot the positive one for you. That is the real low pass filter you can achieve. All right? So it means what? Never mind how high frequency the noise is, after filtering, you still get some portion left. Okay, because you don't have any kind of clear cut, just like this and that. Oh, 1 here, 0 there. Oh, no, sorry for that. Sorry. We are humankind, we are not God, we cannot achieve anything like that. It is totally impossible. The other issue, again, I would like to highlight, nothing is free. If you would like to filter some kind of high frequency noise here, you will have some distortion for your low frequency components. You can see it is not flat. No. Sorry for that. Okay? So you need some distortion. Here, you try to depress the component you dislike. Good. But you cannot cancel. You cannot cancel them totally. No. You can only reduce it. Instead of cancel it, remove it. It's no way. Okay? However, the price you need to pay is distortion for the components you would like to have. That is a so-called trade-off. Okay? Now you may say, hey, I have better shape for such kind of low-pass filter. Butterworth loop filter. Okay, I will plot it again. Sorry, it's something like this. So, do you feel better for the components you would like to have? It still has some distortion here. Maybe for DC, it looks good, okay? But after that, you can see it becomes attenuated. More and more distortion for medium frequency ones, okay? And how about the high frequency component? The attenuation here is the worst, okay? The more beautiful it looks for your low pass band, the slower rate for such kind of high frequency filtering. That's it. You need to pay the price. Nothing is free in analog domain. So you can see, if possible, humankind would like to apply digital filtering instead of analog filtering. Okay, it means from the beginning, we digitize the signal into digital domain, then process everything with digital algorithm. Congratulations. That is a very good idea. But the ugly truth is, if you have RF signal, right, 1 gigahertz, right now maybe 2, 3, in the future 5, 7. Oh, what kind of ADC can survive under such kind of very high frequency with good enough resolution? I cannot say no, but really, really few. And for such kind of very high frequency ADC with good enough resolution, it means very hard to design. Okay? Most of the ADC designers, they cannot achieve in such domain. Sorry for that. Okay? I need to pay the price. Even you can design it, the cost should be sky high. Very, very expensive. Okay? That's it. So, for analog IC designers, don't try to design the best on earth. Yeah, on campus, it's good because we can publish papers. But for companies, sorry, please don't do anything like this. Yeah, much better than the specifications. Are you stupid? You waste a lot of time and money to make it. You will be fired very soon. Okay? No over-design for your companies. Sorry. Please pay attention to that. Don't do any silly things like this. Don't try to prove, I'm much better than the other colleagues. I would like to be promoted just like my student. No. I think he never did any kind of over-design. Good enough means a lot of money for the companies and yourselves. Don't do anything more than that. Okay? And also we need to pay attention to second-order effects. just like channel length modulation, body effect, blah, 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 a lot of such kind of minor issues. Actually, in digital domain, they pay no attention to this. Why? Because they can tolerate a lot of inaccuracy, a lot of error. Okay, but for us, anything existed, anything wrong existed, you cannot remove it totally. No, you can only reduce it. The more you would like to reduce it, the more you need to pay. The time, the money, the effort. Okay? And in analog domain, even till now, almost nothing is automated. What does it mean? We don't have any kind of analog EDA to help you design ADC, DACP, or DR. No. Almost everything needs to be handcrafted. 纯手工打造. Okay? The length, the width, the bias, everything. You need to change it by yourselves. Even more unluckily, for most of the papers, you don't see the real size of the device. They have only circuit. That's it. No detail. You need to try everything by yourself. I think that is a very bad issue in analog domain. But I guess everybody would like to protect his or her own loyalty. So nobody would like to tell you the truth. Okay? Maybe even worse is that they design something with very good performance, but for paper publication, they try to omit some device. Or by purpose, throw something wrong to the circuit to confuse it, to confuse the others. Why? Because they try to keep a safe distance from the others. Yeah, they would like you to spend more time and effort to catch up with them. Then they can do something newer and better. That's it. We compete with each other very, very much. That is really sad. However, it's still, that is bad. For such kind of technology evolution, it will slow down the evolution. However, it is also good. Good for what? Good for you. You design the circuit. Again, you can keep your secret as long, not as long as you like, but longer. If you tell the truth, then everybody know the secrets. They can do the same design. They can become copycats, right? Copy and paste to their own chip design. Then you lose the battleground with all of them, right? So such kind of bad habit is still a good issue for you to protect your own loyalty, blah, blah, blah. That is some kind of ugly truth you need to face in analog IC design. Nobody would like to tell you the truth unless you're buddies. Okay? You like each other. You would like to help each other. Who? Your supervisors, your mentors, your bosses in the company. If you behave well, then you can get more secrets from your seniors, your supervisors, your bosses. So, in this field, please pretend to be nice, okay, to be humble. Don't do anything from the very beginning. Oh, look, I'm so outstanding. Oh, my IQ is better than you. Oh, sorry for that. You need to do everything by yourself. Nobody will tell you the truth. Okay? For each run, you can see on campus how many batches you can have for the same process. Maybe four batches for each process per year. Okay? So if you make something wrong, then you need to wait for the other batch, or for your chips to come back, measure, something wrong, then redesign for how many months. And after that, you need to wait for the newest batch. Then after application, you need to wait for 3.5, on average, 3.5 months to get the newer chips back and measured. It's wrong again, right? So how many years you need to make everything right? Ridiculous. So you had better be humble, be nice, then you can learn all the secrets from the others. All right? So it means that the hierarchy in analog IC design is more solid, more robust than in digital domain, because what you see is what you get in digital domain. If you are smart, if you are more intelligent than the others, you can read papers faster than the others, and everything is correct in digital domain. 1 + 1 = 2. Bingo. So IQ in digital domain means something. Means much more in analog domain. Yeah. But in analog domain, EQ means more than IQ. All right? So we need to do a lot of simulation. All right? But we need to get help from the modeling. The models for your devices, blah, blah, blah. And I told you already, usually it is impossible for you to get the circuit detail, the width, the length, blah, blah, blah. No. So what you can do? By guessing. Okay? Depends on your experience. Good. But if you didn't do any design similar to current one, usually you need to depend on your intuition, 直觉. Okay? And this is a very important warning from me to you. If you are not experienced enough, then I warn you, most of your intuition is incorrect. Okay? Don't believe in your intuition. More than 90% of them are incorrect. That is really upset, but it's true. All right? You need to try your very best to debug your own brain for analog IC design. So the best way is still to debug your own brain through the help of the others, your seniors, your supervisor, your bosses, blah, blah, blah. They will tell you, oh, no, don't do something like this because you will make something wrong. You need to turn your way to the other side, blah, blah, blah. Okay? Anyhow, we need some novel circuit and architecture to achieve high performance. It's really important in analog IC design. Yeah, this is, for example, the delay for an inverter, another gate. Piece of cake, right? But you can see, that is current situation. In the past, it was, we have the so-called, for simulation, we have the so-called 5 corners, FF, TT, SS. That is for the delay, right? The slower the process is, the longer delay. The faster, the shorter delay. Wow, anybody knows that? So in the past, you only simulate 5 corners, here, and there, to make sure nothing wrong, right? But this is the real measurement. You only simulate 5 points, right? The so-called 5 corners. Is it good enough? No. You can see? The real measured delay spread all over such kind of 5-corner area. They could be here, over there. Wow, totally possible. All right? 5 cases out of almost infinite. 无限多种可能里面，你只模拟5种，你敢跟我说你的电路会够好 ？Forget about it. It is totally impossible. Okay? That is the ugly truth. In the past, maybe the measurement, the real measurement, maybe around here, around there, some points some points. Okay, but nowadays, according to random mismatch, the more serious random mismatch for current processes to make all of them, I mean the 5 corners, mix up with each other. 全部混在一起了，你看不到5个点了，全部混在一起了。So you need to pay more attention to mismatch. That is the lesson you can learn from such kind of measurement result. Okay, and then why would like to integrate everything on the same chip for cost reduction? That's it. Okay, and why we choose CMOS? Because, not because its performance is the best. No, sorry for that. The truth is, we can achieve less power consumption with CMOS design. All right, and CMOS process right now can be easily scaled down. Very good. Okay, and we pour a lot of money and effort to develop such kind of new processes. It means the evolution for CMOS is much better and faster than all the others. So the fabrication cost on average is, I mean for the same technology, it is the lowest. But its evolution is much faster than the others. So actually, if you focus only on the best process for CMOS, for BiCMOS, for German, for gallium arsenide, blah blah blah. CMOS is still much more expensive, because for all the others they are far beyond. Okay, maybe 4 to 10 or even 20 generations behind our CMOS process. Yeah, I read the news yesterday. TSMC announced that they had a very huge progress for 2 nanometer test run. Yeah, for 2 nanometers, actually, they would like to apply GAA instead of FinFET. All right. For TSMC roadmap, FinFET will survive till 3 nanometers. But for Samsung, it announced that they will apply GAA to 3 nanometer process. So let's wait and see. Yeah, who will dominate the market years later? Anyway, on this page, I would like to tell you something about abstraction. 抽象化. Okay? Why we need such kind of abstraction? Simply because the circuit becomes too complicated to be handled by our own brains. Too complicated. I told you already, for each chip, we have billions of transistors. Okay? How can you design any circuit with billions of transistors? Forget about it. It's totally impossible for humankind. All right? So we need to have such kind of abstraction to simplify the whole circuit. Yeah, just like this. For digital IC designer, they only need to know the whole system, the structure for the whole system. How many blocks they need to have? Then they describe, for example, I need 40-bit multiplier, right? 128-bit accumulator, blah, blah, blah. They only write it down. That's it. But how to realize it? Not their business. EDA tools can help them. All right? They don't need to know what is the real circuit. Should be for such kind of 64-bit something, 128-bit something. Sorry for that. They don't need to be bothered. All right? Only EDA tools should be bothered. That's it. So for them, usually they only focus on system level or architectural level. That's it. good enough. Right? For example, adder, we have many kind of adders, right? Bubble adder, synchronous adder, blah, 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 blah. Okay, as you like. They can choose different architectures to implement the overall system. However, even they would like to apply a bubble counter, right? Do they need to know the real circuit? No, usually not. No. Okay? So I always told you, digital IC designers, they can live happily since after what? After they learn something, they can apply the concept again and again. Yeah, from 0.18 micron all the way to 5 nanometers, 2 nanometers. They can write the same code. What? You can. EDA tools can carry the heavy duties for all of them. However, on the contrary, our lives are much miserable than theirs. We need to focus not only on circuit, we need to focus even on device. Again, the width, the length, all the capacitance, the resistance, the current, the bias current. We need to take care of all the detail. I don't think you can design from here to there. No. For their design, we call it top down. The top to here, then for the details will be dealt with by EDA tools. And how about us? Bottom up, from the smallest device all the way to the whole system. You need to design it by yourself. All right? That is really bad. But again, it is also very good for you. Why? Because you are so important. Nobody can replace you. Right? You need to do such kind of dirty jobs. How about your bosses? Just like me. I wouldn't like to touch anything like this. All the dirty jobs go to my students. I only stay here to tell them what is my logic thinking, what I would like to have. Right? Then my students need to go to the bottom, then all the way to realize the whole system I would like to have. Okay? So if I don't have any student, zero production, zero performance will come out of my lab. For digital design professors, I guess they can do something by themselves. Right? Oh, for some of our analog IC design professors, just like Professor Zhong, or Professor Lu Zhiwen, Professor Lu, they can design their own chips. Professor Lu even told me, he could do the layout by himself. What is life? Really, really poor. Yeah. So even his publication is much better than mine. I would still like to enjoy my own life. Yeah. That's too hard for me. And this is some kind of IC design flow. Well, from the very beginning, TSMC, UMC, Samsung, they try to develop new technology. So they need to have a lot of test run. Okay? They will have a lot of test keys, 测试元件, during test run. For what? To measure the performance, to extract the models. And also, for the layout, they need to know how wide the layout, the layer could be. For metal, for polysilicon, for everything, how wide and what is the spacing, how close they can get. Okay? Yeah. So, for such kind of test run, they not only extract the models for devices, for all the transistor, resistor, capacitor, everything, and then they need to know the design rules for layout. Right? And for designers, they only need to know the device model. They can design their own circuit and simulate the so-called pre-simulation to know the performance. But after that, we need to do the layout. Should the help of design rules, right? Then if nothing wrong for DRC, design rule check, then you can do post simulation. If nothing wrong, then we can go for a tap out. If something wrong, then you need to go back to redesign your circuit or to redo the layout, blah, blah, blah. Usually, if the performance is close to what you expect, then you may only change your layout, all right? But if there is a huge gap between your post simulation and your specifications, you had better go back to redesign your circuit. Okay, not only redo the layout, it's far less than enough. And allow me to show you some of the tendencies. You can see, this is for digital chips. The supply voltage goes down all the way. All right? It becomes smaller and smaller and smaller for each new process. And how about analog IC chips? Oh, sorry for that. You can see we stay with the same, we play with the same supply voltages for quite many years, then goes down a little bit. Why? Because we don't have enough innovation to push down the supply voltage. The lower supply voltage usually means much harder to design. Not only harder to design, no, much, much harder to design. So we need to play with the same supply voltages for quite a long time until somebody, just like Einstein in this field, to create something new, to create something brand new to help us go further into lower supply voltage domain. 我们需要类似爱因斯坦如此聪明的人，才能够帮我们往下推啊。But you may be curious, hey, for the same chip, right? Our digital cores, the supply voltage for our digital cores goes down annually or seasonally. Okay, 每年或每季都一直往下掉。But how about us? We still play with the same supply voltage. Why? Because we don't have innovation, good enough innovation to push down the supply voltage. And how? How can we survive with such kind of digital circuit with much lower supply voltage? We need the so-called analog-friendly devices. Usually, we call it thick MOS. 我们需要比较厚的 MOS. To play with higher supply voltage, the thickness of the gate oxide cannot be too thin. If it is too thin, then the supply voltage, the spikes, the ripples of your supply voltage may cause a serious damage for your MOS gate, for the gate oxide, sorry. Okay. And after that, it will become malfunctional or it doesn't work anymore. All right? So, analog-friendly devices, yeah, it's good for us. Then we can play with the higher supply voltage. Okay, we don't need to go down with such kind of low digital supply voltage. We can live happily since after. But nothing is free. You need to pay a lot of money, much, much more money than this. The thicker the gate oxide is, means what? The much larger the MOSFET will become. Okay? 越厚的电晶体，它的尺寸会变得非常非常的可怕。You can see, even for maybe 5 nanometer process, we can still use some MOS which can tolerate maybe 1.8 volt. Wow. 1.8 volt means what? It belongs to 0.18 micron error or 180 nanometers. On the 5 nanometer chip, you still apply some bulky transistor in 180 nanometer era. Wow, what is the transistor size? Terrible. The width and the length. See? Am I right? Yes. 36 times larger. That is for the width and the length, right? So how about the size? Oh gosh. Almost 1,000 times larger than the smallest one, than the so-called regular MOS. Because in 5 nanometer, wow, the gate oxide is so thin. It can only operate maybe at 0.5 volt, 0.4 volt. I have no idea, right? But the size is only 1,000th of this one. So if you would like to apply such kind of analog-friendly devices, it means your boss, your company, will lose a lot of money for that. Okay? It's friendly to you, but it's really unfriendly to your company. I mean, according to money making, it doesn't make any sense. Yeah. So, this plot is from my very good friend, Professor Chen, 交大陈克宏教授啊，非常要好的朋友哈。Once upon a time, he published one paper, and he showed such kind of cartoon to show how hard in analog domain, to lower down the supply voltage, because we don't have good enough innovation. We try to resist, okay, all such kind of supply voltage lowering. We fight back. No, don't push the voltage down because we cannot survive. But how about the digital designers? They live happily. They don't care. Wow. They have a lot of tolerance for such kind of high or low supply voltage. They don't care. We care very, very much. So our lifestyles are totally different. Again, ours are much, much harder than theirs. They enjoy their life very much. But again, it is also bad for them because they can be replaced easily. In the past, if something wrong for the market, just like a pandemic, you cannot sell your chairs as good as in the past. You need to fire somebody. In digital design team, the managers, they don't fire themselves, right? And they wouldn't like to fire the bottom ones because they are much cheaper. So they fire the medium layer engineers. Yeah, maybe they are already 40-something or even 50-something. After being laid off, it's very hard for them to find new jobs. That is the story. That is their life they need to face. Okay, if nothing wrong, they can live happily. But if something wrong, the middleman will be laid off. The life will become very, very rushed, very, very hard. Okay? How about here? Again, managers wouldn't like to fire themselves. They will try to fire the mid-level engineers, but for such kind of middlemen, they have a lot of know-how, right? They have no choice. If they fire the mid-level engineers, the company needs to be shut down. It doesn't make any sense. Because, again, the managers, like myself, almost don't do anything, right? Only make the right decision for the company. So what is the right decision? To fire the new engineers because they don't have good enough know-how to help the company survive. So in this era, If you know something important in analog IC design, then you don't need to be worried. You don't need to worry to be fired. No. Okay? So the lifestyles are totally different again. Yeah, they live happily for nothing wrong. Okay, but we can still live not so bad after something wrong. Okay? That is the total different story between each other. Anyway, anyhow, analog friendly devices. Actually, yeah, we don't have very good breakthrough for decades. Okay, now and next decades, don't expect very important breakthrough to help us lower down the supply voltage. No. Yeah. You can see, what do you learn from Professor Razavi, Professor Allen? They have the first edition, the second, the third, blah, blah, blah. Please have a look at the differences. Not much. Okay. About the same. You still learn almost the same ADC structure, almost the same PLL. Yeah. 20 or 30 years ago. Okay. Only very few modifications you can achieve. And this is the reason why we need to stay, we need to play with the same supply voltage for such kind of long time. We need Einstein. But maybe Einstein is 1 out of million. Okay? Or even worse, 1 out of billion. Who knows? I have no idea. Too less Einstein to help us. Okay, anyway, anyhow. Yeah, for such kind of AMS, it means analog and mixed signal technology. You can see the roadmap seems quite pessimistic, right? Because it is not optimistic, because we don't have talented guy good enough to create new structures, new architectures. Anyway, all those materials actually are from my very good friend, Professor Randall Geiger, sorry. Yeah. If you are interested, please have a look at by yourself. That is some kind of brief introduction. All right? Why it is so hard for us to design low supply voltage circuit? Because most of the known technologies cannot survive below 1.1 volt or even below. No. Okay, for example, cascode. All right. If you would like to increase the gain, or later I will show you. All right, let's go further. All right. Here, a brief conclusion. Analog-friendly devices are not our friends. They are our enemies. Because we depend on them, then we cannot scale down the analog circuit. For digital circuit, for the same digital circuit, it becomes smaller and smaller and smaller with new processes. But how about analog devices? No, sorry for that. If you would like to power your analog circuit with 1.8 volt, the size will stay at here, 1.18 microns. The size won't be changed. Maybe only a little bit, not so much. Okay. So your digital circuit can be increased in size. How about analog one? Sorry for that. If you stick to the same supply voltage, the area will be about the same. No much improvement. I mean, in area reduction. Okay? So we need to change our mind in your future design. One of the reasons why, you can see that. For the gain, usually the voltage gain equals GM by RO. GM means what? Conductance from the input to the output. It means we convert input voltage into output current. Right? Then output current by output resistance will become output voltage. So that is the voltage gain, GM by RO. All right? RO means the resistance between D and S. So it becomes the reverse of GO. Okay, GO means GDS. The conductance between drain and source. Okay, so GMRO means what? Briefly, GM by GDS. Got it? All right, and let's have a look. What is GM? What is RO? Okay, you can see here. The slope after saturation. All right? The slope equals 1 over RO. So the larger RO means the smaller slope after saturation for such kind of IV curve. However, you can see that it's really offset. From 0.18, 0.13 to 90 nanometers. Who is 90? This. And which is 0.18 micron? That. Oh. So it means what? The slope becomes larger and larger for newer processes, right? So the RO goes down instead of goes up. It's really upset. And how about GM? Here. Okay. Here, GM over GDS, it means GM by RO. Okay? Yeah. To consider all both effects. You can see who achieved the highest output gain, the voltage gain. You can see the solid line is 0.18. Who is the worst? 90. Really upset. It means what? The better process means the worse voltage gain. The smaller and smaller gain you can achieve with better and better processes. If we go further, here only stop at 19 nanometers. Let's go downward. Even better. 19, 65, 45. Where is 45? This one. That is 90. Okay, so you can see GM, RO goes downward again and again for new processes. Okay. The gain can be even smaller than 10. Oh, that is really upset. So it means what? For the transistor, for new processes, the intrinsic gain, 本质的, I mean by nature, the natural gain is much lower than before, even smaller than 10. See? So it means it's really hard for you to achieve high gain with new processes. But what is the problem? When you learn something called op-amp from your microelectronics, what is the most important parameter for op-amp? Gain. You need to achieve high gain, high enough gain. Why? The other issue is for negative feedback. If you would like to apply negative feedback, you need to sacrifice. Always, instead of usually, no. Or you always need to sacrifice your gain to enhance the other performances. For example, you sacrifice your gain to achieve better stability, higher bandwidth, blah, 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 better linearity, less error. All of them, all such good parameters can only be achieved by sacrificing your gain. So, from the beginning, you need to design an op-amp with high enough gain, then to be sacrificed for negative compensation, negative feedback, right? If from the very beginning, your gain is only 10, nothing can be sacrificed, all right? So it will become much harder than before to design op-amps with high enough gain with new processes. It means what? We need to create new structures for our op-amp. Because op-amp is the so-called building block for analog IC design. Got it? 类比 IC 设计最重要的建构方块、建构基石就是运算放大器。Wow! So we have a lot of bad issues to deal with. Again, for good processes, GM and GO both are degraded. 越来越差，越来越烂。Okay, and also with better processes, VDDs become smaller and smaller. The signal swing becomes smaller than before. In the past, you have 1.8 volt for your signal. Right now, maybe only 0.5, 0.6 volt for your signal. The signal magnitude becomes much smaller than before. How about the noise? The same. Right? The noise have no sympathy for you. 它不会同情你。Oh, look! You guys are so poor. You can only apply 0.5 volt for your signal. So I would like to scale myself down. I'm a good noise. No, sorry for that. All the noise are bad. Okay? They would then like to scale down themselves according to your low supply voltage. Oh, sorry for that. Never mind how large the supply voltage is. I promise you, I warn you, the noise is about the same. The interference is about the same. Okay, so according to signal to noise ratio, noise is about the same. How about your signal? Your signal is reduced from here to there. But this is for power instead of magnitude. So it means what? It's reduced from the squared of 1.8 to the squared of 0.5. So the signal power magnitude is reduced substantially. But again, for noise, the same. So it means it's really hard for you to achieve good enough signal to noise ratio with new processes. And it means what? The effect number of bits, ENOB, will become smaller than before with new processes. Got it? That is true. However, you cannot explain this to your customers. Yeah, you buy new iPhone 12 or new iPhone 13. Apple's engineers will tell the customer, oh, sorry for that, because we apply better processes with lower supply voltages, so the SNR becomes worse, ENOB becomes worse. It means what? The AirPod. If you listen to the wireless earphone, you will get more noise because they use the new processes for customer. What are you talking about? With new process, right? And it means better performance. Don't shit me. I spend a lot of money to buy new iPhone, and you would like to tell me with lower supply voltage? Yeah, the effective number of bits will become smaller, right? So you will listen to more noise than before. It doesn't make any sense. Again, I need to warn you. The expectation from our customer actually becomes higher and higher and higher. But your ENOB with the same structure, with the same design capability, the ENOB will become smaller. But the expectation from the end customers becomes higher. The gap will become larger and larger than before. All right? So it means you need to create something new to fill the gap, to increase instead of decrease the ENOB with new processes. Again, our design becomes much harder than before. And how about digital IC designers? The same, because I told you already. They stay here. See. They stay, oh, sorry. So far away. Oh. All right. Maybe we can have a... Oh. Find it. They only need to stay here. They don't need to care about here or there. Maybe they never know what real supply voltage is. They don't care. Who cares? Idiot to us. We are so lucky. We are so unlucky. But again, that is good for them, but also bad for them because they are much more replaceable than us. Got it? Okay, let's have another break here.